Welcome to Pomodoro Joe for July 24th, 2023. Today we're doing LeetCode problem 50, POW xn. This is a medium problem. Implement POW xn, which calculates x raised to the power of n, i.e. x to the n. All right, that's pretty straightforward. 2 to the 10th, 1024. 2 to the 3rd, 2.1 to the 3rd. 9.261, and 2 to the negative 2. So we'll have to keep negative numbers in mind here, and that will be 1 divided by 2 raised to the power of 2. All right, we've got some constraints, good to know. This should be pretty straightforward. We'll put 25 minutes on the Pomodoro timer and get started. So this is Python. So the simple way to do this is just return POW x to the n. We'll just rely on the internal POW function and just return that. We'll make sure this works, but it should. And we'll submit that. And we're done. Thank you. Thank you very much. I know. Pretty amazing. All right, and this beats 67% of the other. Oh man, that's crazy. So this beats 67% of others for runtime and 41% for memory. All right, let's go back here and see if we can improve on this. Well, we could use a shortcut, which is just x star star n. So this will be the shortcut for that same function. This raises x to the power of n. Let's make sure that still works. It should. This is the internal function, and we'll submit that. And we do pass, but we only beat 26% for runtime and 41% for memory. So not great. Funny, I thought they'd be the same. All right, let's jump back. Okay, so let's assume, for the sake of learning, that they don't want us to use the internal functions, and we actually have to implement our own x to the power of n. All right, let's take a look at this. So we could have some result, set it equal to 0. But before we get there, we might want to do our edge cases. So there's one special case that we want to consider here, and that is if n is 0. So this is one of those things that you probably just had to learn in school. You won't figure this out on your own, but anything to the power of 0 is equal to 1. And honestly, I don't totally know why that is, why they chose to do that. I think it's because when you have something like 2 to the 10th divided by 2 to the 10th, or 2 to the 10th divided by 2 to the 5th. When you do a division of numbers with exponents, you can just subtract the lower exponent from the upper exponent. So 2 to the 10th divided by 2 to the 5th is just 10 minus 5, or 2, let's see, let me explain this again. 2 to the 10th divided by 2 to the 5th, you can subtract the exponent, so 10 minus 5, and then raise 2 to that. So 2 to the power of 5 is your answer. So 2 to the 10th divided by 2 to the 3rd is going to be 2 to the 7th. Now, if you had 2 to the 10th divided by 2 to the 10th, well, anything divided by itself should be 1. But if you just subtract your exponents, 10 minus 10, you'd get 0. So anything to the power of 0 will be 1. So let's handle that here. If n is equal to 0, we'll just return 1. Okay, so that handles that base case. We could also do another one here if we wanted. We could do if n is equal to 1, we can just return x. It helps, why not? Otherwise, we'll have some result, and we can just do a for loop. We could do just for, we don't really need to know what the variable is here, because we're just going to be doing multiplication. So for whatever in range, and we'll go up to n of these loops. All right, let's see, if we had 1, will this be n or n plus 1? We want to do this n times. So if we had 2, we could start this out with x, and then we can just go to n. I think that's better. All right, so for whatever in range n, our result will just be our result times another x. So if we come in here with result starting, let's say it's 2 to the 10th. We'll start this as 2, and it'll be 10. So in our first loop, we'll do 2 times 2, and then we go to 1, or 2, that'll be 4 times 2, and then 2, and so on and so forth. So we get our result. And at the end, we just return our result. So we could do something like this. However, I can already see this is inefficient. We'll try it. Let's just see if this works. Maybe I've got this wrong, but we'll try it out. Yeah, I am off by 1. All right, let's see here. I am doing too many. Interesting. I guess I need to start this as a 1. Oh, but I'm not handling my, oh, right. I have to handle negatives. So we need to do something down here. If n is less than 0, I knew I was doing something wrong. All right, if n is less than 0, we have to change our result now. Our result is going to be 1 divided by, and this will be a floating point divide. So 1 divided by our result. That's right. Negative exponents become fractions. 1 divided by our number to that exponent. All right. We're still getting this wrong? Yes, we're still getting this wrong. Oh man, I'm just failing across the board. So one thing I didn't do is this n is going to be negative. So we're going in range -2. Well, that's not going to work here. So we actually need to flip this n around to be positive. So, all right, if n is less than 0 here, then this n has to be -n to do this, but then we've already lost if n is negative down here. So what if we put this divide inside of here? I think we could probably do that. So the result equals result, going to be like, so in that case, our result would be result 1 divided by x, or we could actually flip our x here. So x will be 1 divided by x. Okay, I think that'll help us. So if n is less than 0, we'll flip our n around to be positive, and we'll flip our x around to be the inverse of x. And then we don't need to do this down here. All right, let's see if this will work. Okay, so now this works. But again, I mentioned this will be inefficient, and I'll show you why. The main thing here, let's say we have 2 to the 10th. So we'll have, or maybe 2 to the 8th, that'll be easier. 2 times 2 times 2. Oh man, we got a bunch of these times 2. So I can already see I have 2 to the 4th here, and I still need 4 more. All right, so this is 2 to the 8th. But just by the fact that I had to do that copy paste means that I'm doing the same operation more than once. So if we did this, 2 to the 8th, we would have to go through 7 operations. That's 1, 2, 3, 4, 5, 6, 7 operations. But I can group these differently. Let's grab these again, group this whole thing. If I group these 2 times 2's, thanks autocomplete. So I can group these 2 times 2. I can group this 2 times 2 here. And then I can keep grouping these 2 times 2. Again, I can just copy and paste this because they're the same. All right, so now I'm grouping these. Same equation, just grouped slightly differently. 2 times 2 times 2 times 2 times 2 times 2. So what if I assign a variable to that? So a is equal to 2 times 2. So that just becomes a times a times a times a. All right, so up here, if I did 2 times 2 times 2 times 2 times 2 up to 8 2's, that's 7 operations. But if I group this 2 times 2, just do this 2 times 2 once, then I've got a times a times a. That becomes 3 operations. So we do this 1, 2 times 2, that's 1 operation, and then 3 more operations. So we go from 7 operations down to 4 operations. We almost cut our work in half. And I can do the same actually with this. If I took these a's, grab that whole thing, and if I group these a's, I already have an a times a here, and then I've got another a times a here. So if I group these a times a's, I can do the same thing. Let's assign b to a times a. So b is equal to a times a. Again, I can just do that once, and then my answer, that's just going to be b times b. Because I have to do, this is b and this is b, so b times b. So now I took this 7 operation problem and I converted it down to, well, I still have to do a times, or I have to still get a, so that's 2 times 2, so that's 1 operation. And then I have to do 2 operations to do a times a to get b, and then I have to do 3 operations. So now I took my 7 operation problem down to 3 operations. And I did that using essentially grouping. Now, I'm not doing any grouping here. I'm doing an O of n operation here. This is an O log n operation because I can divide my problem by 2 each time. I essentially take what would be exponent 8, and I divide it by 2 to get an exponent 4. That's a times a times a times a. That's a to the 4th. And then I divide 4 by 2 to get an exponent 2. That's b squared. So each time I can divide my exponent by 2 and divide my problem essentially in half. So we'll get back to this a little bit later. But for now, let's try. This is our linear operation, O of n operation. Let's see how this goes. All right, it works. Let's see if we can pass. Okay, this is too slow. All right, we passed a bunch of them, but there are 306 test cases. We passed 291, so that's pretty good, but we have, I don't know, an inefficient algorithm. So let's see if we can speed this up. Let's use this test case. Just make sure that we still don't pass, but okay. So we don't pass using this O of n operation. So how can we solve this by dividing the problem in 2 every time? Well, instead of using a for loop, let's use recursion to help us out. All right, let's get rid of this. So we'll still keep our base cases. If n is equal to 0, we return 1. If n is equal to 1, we return x. Now, I guess we can keep our result, but I don't think we'll need this because we'll be doing a recursive function. All right, now we'll keep this. If n is less than 0, we flip n to be positive, and we flip our x to be the inverse of x. So we'll keep that. But now, we will do something a little bit clever here. So we'll be dividing our n by 2 every time. However, if n is odd, we'll basically be dividing our n by 2 and then adding 1. And I'll show you what that means here. So whatever our n is, we can say our result will just be, let's see, well, we'll take myPow. You have to do self.myPow because this function is a method of this solution class. So we do self.myPow. And here we'll pass in our same x, but we'll pass in n divided by 2. And this is an integer divided by 2. So we're dividing our n by 2. So essentially, if this were 8, we're gonna pass in 4. So x to the 4th. That's just like what we had with our a is equal to 2 times 2. And then we have a to the 4th. So this will become our a, and we're going to be dividing our n by 2, but then we do have to take our result and multiply it by itself to get the full answer. All right, so then here we'll have to return result times result. Or actually, let's do this a little bit cleaner. So this gives us x to the n divided by 2, or half of n. We need to get the full n, so our result is really just result times result. Let's do that here. All right, so our full result is the result times the result. So that would be, if this is 2 to the 8th, we divide it by 2. So this will be 2 to the 4th, and to get 2 to the 8th from that, it's 2 to the 4th times 2 to the 4th to give us 2 to the 8th. So this will give us our answer. But what if this is 2 to the 9th? Well, if n is 9, we'll divide 9 by 2 with an integer divide, which gives us 4 again. So this is still 2 to the 4th. So 2 to the 4th times 2 to the 4th. So this will give us 2 to the 8th, but we want 2 to the 9th. What do we have to do? Well, we just have to multiply it by x one more time. So this gives us 4 of our exponent. This gives us another 4, so that's 8. We just need one more in our exponent, so that's just another x. So we'll just do this here. if n mod 2, so that's saying if there's a remainder after we divide n by 2, so this means n is an odd number, then our result will just be our result times 1 more x. And then we can return our result at the end. All right, it's a little bit confusing, but I think if you just look at this, maybe write out some of the math, it should make sense. All right, now let's see if this works. Okay, this works. Let's see if this gives us a better solution than even the native solutions. I think the best we got there was around a 60%. And this does. So now we're at an 83% for runtime and a 7% for memory. So we do a lot better using this recursive solution than we did even with the native PAL. 67 to 83. Yeah. We could probably clean some of this up even more to get a better solution or something even faster. But I'm pretty happy with this. An 83% is not too bad. I'm trying to think what we could do. We could try using cache out here. You want to try that? Let's try that. This might not actually help us, but I don't think it'll hurt us too bad. It's worth a shot. Oh, it hurts us a lot. Now we're down to 28%. I think this hurts us because basically I don't think we'll be ever doing the same. I don't think we'll ever be doing the same sets of inputs again because we're dividing by 2 each time. So I don't think we're ever going to see the same inputs. So this shouldn't actually help us. I'm not too surprised. Okay. Well, we could do simple things, and I don't like doing this necessarily, but let's just do it for fun. So instead of doing these on separate lines, we'll inline them. Now, this is not great programming like style, so I wouldn't recommend this for production code, but for this, let's just play around with it. All right, let's actually flip these around. I know I'm making a lot of changes, but I feel like I'll give this one a little bit more time. All right. Okay, I think this is pretty good. We could do an if here. Yeah, let's do that actually. Well, no, let's just do this. I like this. Holy smokes, that makes a huge difference. That gets us to a 99.4% or 0.04%, I'll be precise. So that gets us to a 99% for runtime and a 41% for memory. So that is the best that I think I'm going to get today. All right, well that's it for me. Hope you enjoyed this, hope you had fun, hope you learned something, hope you can go out and write better code.